In this video, we are going to look at another optimization problem. So here we want to find the point on the curve y equals x squared that is closest to the point 0, 1. Now, this one doesn't say explicitly the maximum or minimum, but it is saying that in some different words, right? So when we read the word closest, we want to find the one, the point that has the minimum distance. And so the point on the curve with the minimum distance to the point 0, 1. So let's draw our picture. We have y equals x squared. That's a parabola with a vertex as 0, 0. Here is the point 0, 1. We want to find the point on this curve that's going to minimize that distance. So, what is the distance between 2 points? Right, so recall our distance formula. The distance formula is the distance between 2 points is the square root in the change in x. Right, so x2 minus x1 squared plus the change in y squared, y2 minus y1 squared. So that is our distance formula. Actually, maybe I'll call that lowercase distance d. In this problem, what is our value of x1 and x2? Sorry, x1 and y1, and then x2 and y2. So x1, y1, we'll have that be the point 0, 1. And then x2, y2, that's going to be just some random point on this curve. Now, when I say random point, I don't mean pick some specific point. I mean, we're going to identify a generic x value. So the x value is x. What is the y value of the corresponding point? Well, that y value is going to be x squared. So whatever the x value is, squared. And so our distance formula that we have on this problem, we are trying to find the minimum of x minus 0 squared plus x squared minus 1 squared. So we want to find the distance there, the minimum distance. If we FOIL this out, multiply these things out, we'll have x squared plus x to the 4th minus 2x squared plus 1. So we have x to the 4th minus x squared plus 1. And now, you can take the derivative of this and try to find our maximum that way. That's perfectly acceptable. But I want you to notice a mathematical trick that we can do. You certainly don't have to, but it will save you some time if you can make this observation. So what are we trying to do? Well, we want to find the value that minimizes this square root. So what's going to minimize this square root? Well, this square root is going to be minimized when the stuff underneath the square root is minimized. So this is why earlier I changed from the capital letter D to a lowercase letter d, because I'm going to, instead of taking a derivative of this, I'm going to try to find the minimum of the stuff underneath. Because if I make that as small as I can, then the square root of that is also going to be as small as it can possibly be. Right. So that's what we're going to look for. Now, there are some observations, some things I should observe that that value has to be positive, but because of this distance formula, we have some squared value here plus a squared value here. This should result in a positive value, and so we should be fine. All right, so let's take the derivative of this modified thing. We'll have 4x cubed minus 2x. So that's our derivative. What are we going to do with that derivative? We're going to set it equal to 0. You could factor out of that thing a 2x. And that would leave you with a 2x squared minus 1. And so x is 0, or x is plus or minus 1 over the square root of 2. So that's what we have as some potential solutions. So let's determine which one of those are the maximums or minimums. So we need to do, for this function capital D, we are going to do a sign chart. We can go from negative infinity up to negative 1 over square root of 2. From negative 1 over square root of 2 up to 0. From 0 to positive 1 over the square root of 2. And 1 over square root of 2 up to infinity. So we're doing a sign chart there. If we choose something smaller to the left of negative 1 over the square root of 2, we will get a sign for the derivative that is negative. Choose something between negative 1 over the square root of 2 and 0. You'll get a positive value and a negative. Excuse me. And then a positive. So, what does that tell us? Well, it tells us right at this point we go from decreasing to increasing, so we must be at a minimum. Here we're increasing to decreasing, so we're at a maximum. Decreasing to increasing, so again we have a minimum. And what are we trying to find? We're trying to find the point that is closest, so the point that minimizes that distance. So if we were to look at the value of D and plug in negative 1 over root 2, plugging in negative 1 over root 2, that distance formula is x to the 4th minus x squared plus 1. We can observe that that is going to be exactly the same as what you would get when you plug in positive 1 over square root of 2. Those two distances are identical. So the 2 points when x is negative 1 over root 2 or when x is positive 1 over root 2, the distances to the point 1, 0 should be equal. So our closest points they are negative 1 over root 2, comma 1/2. So you could also write that as negative root 2 over 2 if you were to rationalize that denominator. And also positive 1 over root 2. You might ask, where did the 1/2 come from? That's just coming from plugging this x value into our original equation. So these are the two closest points. And this is the distance that we have. Excellent. Come back for one more video where we do one more optimization problem. We will see you there.